Hello, all. Welcome to the third session of the semiconductors. In the last session, we had studied about PN junction, majority carriers, minority carriers, depletion layer, barrier potential, electric field. Today, we'll be talking about semiconductor diode. As you can see in the figure, a PN junction diode and its corresponding symbol is shown in the second figure. So, what is a semiconductor diode? A semiconductor diode is basically a PN junction diode with metallic contacts provided at the ends for application of the external voltage, which is clearly shown in figure 1. The symbolic representation is shown in the figure 2. The P type is called as anode and the N type is called as the cathode. What is forward bias of the PN junction? Positive of the battery as shown in the figure is connected to the P type and the negative of the battery is connected to the N type. This applied external voltage opposes the internal barrier potential. In the last class, we have already studied about barrier potential. So, when the external voltage is applied to the PN junction, it opposes the internal barrier potential. Hence, the depletion layer width decreases. Majority carriers, that is, holes from the P and the electrons from the N side, cross the junction easily. The diffusion current is greater than the drift current, and a significant flow of current, which is exponential with the voltage, takes place, which is measured in the milliampere range. What is reverse bias condition? In the reverse bias operation, the negative of the battery is connected to the P type and the positive of the battery is connected to the N type. The majority current movement is opposed, and the current that flows is a contribution of the minority carriers. A reverse saturation current flows, which is in the range of microampere. Let us go a bit into explanation of the same. Forward bias, we have already seen that the positive terminal of an external battery is connected to the P and negative is connected to the N. The applied electric field, that is V, it opposes the internal electric field, which is denoted by V naught. Here, the applied electric field V is equal to Vf, F meaning is forward bias condition. The result is that the width of the depletion layer decreases. Therefore, the majority carriers gain enough energy to cross the narrow junction barrier, and hence the current flows easily once the applied voltage exceeds the cut-in voltage, which is 0.7 for silicon and 0.3 for germanium. In the reverse bias, we already know that the positive terminal of the DC battery is connected to the N region and negative to the P. The applied voltage here is denoted as V is equal to VR because it is for the reverse bias. This electric applied field aligns with and reinforces the internal barrier potential, giving rise to the widening of the depletion layer. Therefore, the majority carriers are pulled away from the junction by the battery terminals, preventing them from crossing. That means there will be no diffusion now. No majority carriers cross the junction. Hence, the majority current is almost zero and a very negligible reverse saturation current flows due to the minority carriers. Now, these minority carriers are because of the thermally generated electrons in the p region and holes in the n region. Since it is very, very low, very negligible, it is measured in microampere for germanium and nanoamperes for silicon. A bit more about the barrier potential. Let the applied voltage be V as indicated by VF for the forward bias, and the internal barrier potential be given by V naught. What happens in the forward bias condition? The applied electric field opposes the internal barrier potential, causing decrease in the depletion layer, and the effective barrier height lowers to V naught minus V. That means as V increases, the barrier height decreases. What about reverse bias? The applied electric field, here indicated as V is equal to VR, for the reverse bias, it aligns and reinforces the internal barrier potential. This causes the depletion layer width to widen, and therefore the barrier height now increases to V0 plus V. That means with the application or increase in the reverse bias voltage, the barrier width height increases. Let us now learn about the characteristics of the diode. To know about characteristics of the diode, we have to take into account both the forward bias condition of the diode and the reverse bias condition of the diode. You can see that the graph is shown for VI characteristics. That means what is the relation between the applied voltage and the corresponding current that flows through the diode. The graph is shown for the behavior of the semiconductor diode in the first quadrant and the second quadrant. Let us now know more about what is meant by Vk. What is Vk? It is a cut-in voltage. It is 0.7 volt for silicon and 0.3 volt for germanium. That means whenever the semiconductor diode is forward bias, there will be flow of current only when the applied voltage exceeds this cut-in voltage. Forward bias characteristics. We already know that the P side is connected to positive and N side is connected to the negative terminal of the supply. V is equal to Vf for forward bias. Now, when the applied voltage is less than the cut-in voltage Vk, the current remains negligible because the applied potential is very small as compared to the built-in barrier potential, that is V naught. Now, what is cut-in voltage? The minimum forward voltage at which the potential barrier is completely neutralized and current begins to rise sharply. This is indicated by Vk, and as told to you earlier, it is zero point 0.7 for silicon and zero point 0.3 for germanium. Therefore, once the applied voltage is greater than Vk, the barrier height drops to V0 minus V. The depletion layer now narrows and the majority carriers diffuse rapidly across the junction, causing current to increase exponentially, which is measured in milliamperes. The reverse bias characteristics. We already know P side is connected to the negative terminal and N side is connected to the positive terminal of the battery. Now, the applied potential reinforces the barrier potential to V naught plus V. That means the depletion layer is widened and it blocks the majority current flow. Very small, almost negligible current flows due to thermally generated minority carriers. This is measured in microamperes for germanium and nanoamperes for silicon. What is VBR? Reverse breakdown voltage. If the reverse voltage is increased beyond a threshold, the junction breaks down and the current increases abruptly, as shown in the third quadrant of the graph. If you'd like to know more about semiconductors, electronics, do join Goal Guru. In the next class, we'll be talking about applications of the semiconductor diode. Thank you.